we had a brief, not really that brief, but a stint with charges and the effects that they could produce while at rest. And their electrical interactions, right? Electrical interactions were largely related to charges at rest, and they were characterized by what we refer to as an electric field, right? The motion of the charge in that context was inconsequential. It didn't matter, right? The force that a charge experienced in an electric field produced, let's say, by some of the charges, that was the electrical interaction that I'm referring to, had nothing to do with their motion. That was the electrical force experienced. The electrical interactions had no bearing on the motion of the charges. Now, charges, however, can experience forces because of their motion. Forces because of their motion. Or produce interactions because of their motion. Now, what they do in effect when they move, when charges move, what they do in effect because of their motion is really a magnetic interaction or a magnetic field. A magnetic field is what they produce when they are moving. And this magnetic field is a representation of the magnetic interaction, right? Like the electric field was a measure of the electrical interaction, the magnetic field B will be a measure of the magnetic interaction. If there is a charge Q and it has a velocity V as perceived by an observer, if it has a velocity V as perceived by an observer O, say this is an observer O, different observers would perceive different velocities of the charged particle depending on their own velocities. Let's say this observer O perceives a velocity V on this charge Q. Then at a point P, whose position vector with respect to the charge is R, the magnetic field or the magnetic interaction produced by this charge Q at this point P, and as reported by this observer O, is found to be given by mu naught by 4 pi Q V cross R divided by R cubed, where this mu naught is said to be the permeability of the medium or permeability of vacuum. The unit of measurement of B, the SI unit of measurement of B is what's referred to as Tesla. That's the SI unit. The CGS unit of the measurement of B is what's called Gauss. A Gauss is like a 10 to power minus 4 Tesla T. We will hardly deal with Gauss. The unit of measurement would be Tesla. We will work in the SI framework. This mu naught, of course, you know, there is a lot of connotation around mu naught, but we will not get into too much around that at this point of time. But just a brief mention that mu naught by 4 pi has a value equal to 10 to power minus 7 SI units. 10 to power minus 7 SI units is what mu naught by 4 pi would have. This 4 pi is artificially inseminated in this whole mathematics so that so that down the line you will realize that there is a 4 pi that will appear in the numerator, will cancel off this 4 pi, and it becomes an algebraic simpler entity to deal with. This 4 pi only has algebraic implication. It has no physical implication per se. It's just to make the algebra look a little neater and less messier. Now, of course, this is all for vacuum. If it was some other medium, then other media would have what's called relative permeability. Mu r is relative permeability, which is a property of a medium. For vacuum, it will be 1. For other medium, it will have a value other than 1. So, if it was some other medium, then this mu naught would be replaced by mu naught into mu r. This mu naught would be replaced by mu naught into mu r, where mu r is the relative permeability of the medium. So now, of course, by default, we will look at air or vacuum to deal with until and unless otherwise stipulated. So very clearly, since this V depends on the observer who's reporting B at the point P, this B, the magnetic field produced by a moving charge, the magnetic field B produced by a moving charge is frame dependent, very clearly. This magnetic field produced by a charge moving charge is frame dependent, There are quite a few deep issues associated with these stories, but too early to right away get you into the thick of those things. But for the time being, let me also say that if this observer was moving with the same velocity as the charge, then at P the magnetic field reported would be 0, because the relative velocity, this V is the relative velocity, that's going to be 0. Now if a charge Q produce a magnetic field B, then in presence of some other magnetic field, a moving charge can experience a force, can interact with the B that it is in because of something else or some other effect, right? A charge Q could be moving in a region. A charge Q could be moving in a region that has a magnetic field B associated with it, and this moving charge will experience a force in the magnetic field in which it is housed, to which it is exposed. In fact, if a charge Q that has a velocity V is exposed to a magnetic field B that could have been produced. See, it produces its own magnetic field, but it could also be exposed to the magnetic field of some other moving charges or some other magnets, right? So then, when it's exposed to a magnetic field B, then this charge is found to experience a force F, which is Q into V cross P. That's the force experienced by a charge Q when exposed to a magnetic field B, right? Very clearly, this force F is perpendicular to the plane containing V and B, and will therefore be perpendicular to V, say, the velocity of the particle. This force, the magnetic force that the charge experiences, will be perpendicular to V, and therefore F dot V will be 0. That means the power associated with this magnetic force will be 0. So the power associated with the magnetic force is 0. That means the work done by the magnetic force is 0. right? That means magnetic forces will never do any work. In a loose context, they are lazy forces. And if they cannot do any work, they are incapable of changing the kinetic energy of particles. Because work energy theorem, kinetic energy would change if there is work done. If work done is zero, change in kinetic energy brought about is zero. So, when exposed to a magnetic field B, a moving charge will maintain its kinetic energy. It will maintain its speed. Very clearly, the force F is non-zero. The force F is non-zero in a general sense. It's perpendicular to the plane containing V and B. Now, a force perpendicular to the velocity cannot change the magnitude of the velocity. It can only change the direction of the velocity. The speed will remain the same, but the velocity will not remain the same in general, right? One small distinction between a magnetic field and an electric field. If there is a charge Q and it's exposed to an electric field E, it will experience a force in the direction of E. The force experience will be in the direction of E if Q is positive, and opposite to E if Q is negative, right? But in this case, the force because of a magnetic field is not in the same direction as B. It will be perpendicular to B, right? So, when we talk of an electric field, then the electric field would be synonymous with electric lines of force. But when we talk of a magnetic field B, a magnetic field line will not be synonymous with magnetic lines of force. Just like in an electric field, the tangent, and in an electric line of force, the tangent at any point will give me the direction of the electrical force at that point. If I have a magnetic field line, then the tangent to a magnetic field line will not give me the direction of the magnetic force. Yes or no? Do you all understand this fact? Right? So, we talk of a magnetic field line, and which is not the same as the magnetic line of force. But when we talk of an electric field line, that's synonymous with an electric line of force. Clear? Now, the magnetic field, like I said, produced by a moving charge, just the way a charge exposed to a magnetic field B will experience a force. I said a moving charge will produce its own magnetic field, whose value will depend on the observer, a frame dependent magnetic field produced by a moving charge. Mu naught by 4 pi Q V cross R by R cube, like I told you. Now, if instead of a moving charge, we had a current carrying conductor. If we had a current carrying conductor, if this was a current carrying conductor, and say it carried a current I, okay, then it has electrons which are negative charge carriers, and then the atoms, or the atoms deprived of the electron, were the ions that would be positively charged, and in any given length the density of electrons and the density of these positive ions would be the same. Yes or no? Right? Now, if the current is like this, which is the conventional current, then the electronic current, as you know, is opposite to the direction of the conventional current. Electrons move in this direction, whereas we take the conventional current to be moving in opposite direction, right? So if there is a electron, say, right, which actually promotes current, and it has a drift velocity Vd. If it has a drift velocity Vd, and there is an observer O. There is an observer O, right? And the observer O moves in the direction of the electron with a velocity Vd, right? Then the magnetic field produced by the electron at various points as perceived by O will be 0, because there is no relative motion between these electrons and this observer, right? No relative motion. So the magnetic field produced by these electrons as perceived by the observer will be 0. However, it's as if the observer moves like this, see, the positive ions are at rest with respect to the wire. The positive ions with respect to the wire are at rest. It's only the electrons that move. Yes or no? The deprived positive ions would be at rest with respect to the wire. Yes or no? Right? However, when the observer moves like this with a velocity Vd, the positive ions would seem to be moving up with a velocity Vd with respect to this observer. And they would produce a non-zero magnetic field. And since the density of electrons in any length is the same as the density of the positive ions across that length, the magnetic field that these positive ions would produce at a given point is the same as the magnetic field that these electrons would have produced because of their motion. Yes or no? Which means now, if there is a current, then the magnetic field perceived by this observer would be frame independent, even if the observer had a velocity, right? Any change brought about because of the velocity of the observer would be compensated by the relative motion as seen on the positive ions, and the magnetic field produced at any point O would be rendered frame independent. So even though discrete charges would produce magnetic fields that are frame dependent, currents will produce magnetic fields that are frame independent. That's the key. Discrete charges would produce magnetic fields that are frame dependent, whereas continuous stream of charges, as in a current in a metal, will produce magnetic fields that are frame independent. In fact, the manner in which the magnetic field is computed by a current I or current carrying element I is given by Biot-Savart law. Let me tell you the magnetic field produced by a current carrying conductor. So, if this is a current carrying element, small current carrying element carrying a current I, if this is a small current carrying element carrying a current I, and you know the way you designate this element is a tangent dl. dl is the length of the conductor. The dl vector would be along the tangent to this element, would be along the tangent to this current carrying element. Then this current carrying element at a point P, which is located by this position vector r of P as seen by this element dl, then the magnetic field produced at P because of this dl is given by what's called Biot-Savart law. The magnetic field dB produced by a small current carrying element dl is given by mu naught by 4 pi I dl cross r by r cube. That's Biot-Savart law. Very clearly, dB will be perpendicular to the plane containing dl and r. In this case, dl is like this, r is like this. So dl cross r would be into the plane of the paper. So the plane of the board in this case. So the magnetic field produced by this dl at this point P, with this being the direction of current, is into the plane of the board, right? Now, so this is by a small element dl of a conductor, right? Suppose we had a finite conductor. We had a finite conductor. Then every element of that conductor would produce a magnetic field at a point P, and then we would have to undertake responsibility to vectorially add the dBs produced by various dls. Either vectorially add, or if all the dBs are in the same direction, add them like I add scalars, right? So, so then, if this was a finite current carrying conductor, then what I do is I break this conductor into infinite number of these dls. For each dl, I perform like a mu naught by 4 pi I dl cross r by r cube. That's Biot-Savart law. That's the dB produced by each dl. At the point P, and then I do a vector summation of all the dBs at the point P. That's going to be the net magnetic field at the point P. This summation carried out by taking all the dls from A to M, From point A to M, I do take all the dBs and carry out a vector summation of all these dBs, right? Now, let me look at computation of magnetic field for some regular geometries first, right? I'm first going to examine a finite length of a straight wire and a finite length of that straight wire, okay? Say this was a wire P to Q, or say M to N. And it carried a current I, say. Clear? And at this point P, I want to be able to compute the magnetic field produced by this finite Mn, finite straight Mn. Okay. First of all, let me locate P. P could be located, let's say, with the help of two angles, alpha and beta. Alpha and beta would locate P, right? And say P was at a distance R. Perpendicular distance from this wire was R. Let's say F was the foot of the perpendicular from P onto the wire. I now want to be able to compute the magnetic field at P using Biot-Savart law by breaking this finite wire into infinity of these dls starting from M all the way to N, and carry out a summation of all the dBs produced by various dls, right? That's the objective. So first of all, from this foot, I at a distance L, let me select a small element dl. dl is the magnitude of the element. All the dls would be in the direction of the current. current, starting from M all the way to N. Clear? And then for this DL, let me do a magnetic field computation at the point P, and then sum it up by taking points, all the DLs from M to N. Let me carry out a conventional summation of all the dBs, the magnetic fields, right? So then say at this point P, this is my L, and say this is my theta, this is the DL, the direction of DL is like this, and the position vector of P with respect to this DL would be this, and would have magnitude R. Yes or no? Right? See, this point is C. The magnitude of dB produced at P is going to be what? Because of this DL, the magnitude of dB produced is going to be mu naught by 4 pi I. The current carrying by this DL is I. And then DL is like this, right? This is the point P. This is the vector R. So DL cross R would be into the plane of the board, right? And this is theta. So angle between DL and R is going to be pi minus theta. The angle between DL and R is going to be pi minus theta, right? So then mu naught by 4 pi I, DL cross R would be like DL into R into sine pi minus theta, but sine pi minus theta is sine theta. So that's going to be DL into R into sine pi minus theta, which is sine theta, divided by R cube. That's the magnitude of the DL. That's the magnitude of the dB. That's the magnitude of the dB produced at P by this chosen DL, right? And the direction of dB, realize this is DL, this is R. DL cross R is into the plane of the board, yes or no? So the direction of this dB is into the plane of the board. Yes or no? All these DLs therefore produced field into the plane of the board. So the direction of all the dBs is the same. So I can add all the dBs like I add scalars, right? So the net B at the point P would be the scalar summation of these dBs because they are all into the plane of the board, right? So the net field produced at the point P, the net field produced at the point P by this current carrying wire would be sum of all of this mu naught I by 4 pi. See, this R and this R will get cancelled, so 1 R squared DL by R squared into sine theta, and this integral to be taken so that every DL from M to N could get included. That means if I could make theta the subject of integration, if I could make theta the subject of integration, then how would theta vary? At M, what is theta, and at N, theta will be beta? At N, theta would be beta. And at M, what would be theta? Pi minus alpha. Realize that at M, this is the angle that you would have to take. This is the position vector. This would be my theta. Yes or no? Right? So theta varies from pi minus alpha. Theta varies from pi minus alpha to beta. Yes or no? I hope all of you understand why theta varies from pi minus alpha to beta. So theta varies from pi minus alpha to beta. Realize how theta has been selected, right? On this side of the position vector, on this side of the position vector, right? So if this was the position vector from M, then on this side of the position vector, theta is pi minus alpha. That's why pi minus alpha to beta. So then the last bit that remains in this context is computation of this integral, right? By making theta my subject of integration, both dl and small r, both dl and small r would have to be expressed exclusively in terms of theta, and then we carry out a regulation integration. Yes or no? So See, this distance is r. This is r. So would you mind believing that small r is capital R cosec theta? Right? And small r is capital R cot theta? Small l would be capital R cot theta, right? And therefore, dl, the differential element dl, would be minus r cosec square theta d theta. Yes or no? So now I can write dl in terms of theta, I can write small r in terms of theta and carry this integration out. Clear? Now see what it becomes. This would be like mu naught I by 4 pi integral pi minus alpha to beta. This dl is minus r cosec square theta d theta. And of course there is a sine theta here, d theta divided by r squared. R squared is capital R squared. Right? Then, so the B would become minus mu naught I by 4 pi r integral sine theta d theta, right? But integral sine theta would be minus cos theta, so this will become plus. So that's going to be cos theta, where theta runs from pi minus alpha to beta. Yes or no? Right? If the current was going like this, all the dls will produce a magnetic field into the plane of the board. So this net B at P is going to be into the plane of the board. It's going to be into the plane of the board. If the current were to be flowing like this, then the net B at the point P would be out of the plane of the board. That is what, because all the dls will change direction, so all the dl cross r's would change direction. Right? So which then turns out to be, as you can very easily see, mu naught I by 2 pi r cos alpha plus cos c, minus cos pi minus alpha will become plus cos alpha plus cos beta by 2. That's how you can write this. Mu naught I by 2 pi r cos alpha plus cos beta by 2. That's a magnetic field at the point P located by these angles alpha and beta, and this point P being at a distance capital R from this straight current carrying wire. Clear? Now, suppose this wire is made longer and longer and longer. Then what happens to these alphas? They become smaller and smaller and smaller. The longer the wire, the smaller the values of alpha and beta, right? So, if alpha tends to 0 and if beta tends to 0, then the wire will become infinitely long. Yes or no? Then this would mean it's an infinitely long wire. Then the magnetic field at a distance r is going to be given by mu naught I by 2 pi r cos 0 plus cos 0 by 2. This will become 1, right? So the magnetic field then at a distance r for an infinitely long wire is going to be mu naught I divided by 2 pi r. Right? So far so good, right? These are all regular results, and you would have to take notice of all these results. Can I? Yes. Diptesh, you have a question? Settled? So realistically then, realistically, say if there was a current carrying wire I like this, infinitely long current carrying wire like this, then at this point P, see all the DLs will be like this, all the R's will be like this, so the DL cross R's would be into the plane. So at points P to the right of this current carrying wire, the field would be into the plane of the board. However, if you look at points Q to the left of this current carrying wire, then my DLs will be like this, my R's would be like this, and the DL cross R's would come out of the plane of the board. That means at Q, it will be out of the plane of the board. So points to the right of this wire, if it carries current upwards, would be into the plane, and points to the left, it's going to be out of the plane of the board. Yes or no? Right? In fact, if I imagine a circular loop of radius capital R surrounding this, right, of radius capital R surrounding this, then let's say at this point P, the magnetic field will be into the plane of the board. See, this is the circular loop of which this becomes the axis. This is a circular loop of which this is the axis. Then the field at P would be into the plane of the board and will be along the tangent to the loop, will be along the tangent to the loop at P. In fact, the magnetic field at every point will be along the tangent to the loop because it has to be perpendicular to R. DL cross R, so because it has to be perpendicular to R. So the magnetic field at P tangent to the loop, if I take a point here, the magnetic field will be like this. If I take a point here, the magnetic field will be like this. If I take a point here, so at every point of this loop, the magnetic field would be of the same magnitude, which would be mu naught I by 2 pi R, and would be along the tangent to the loop, and will be along the tangent to the loop. Right? And the way you can remember this is, if you take your hand, if this is the only right hand you have, right, and you curl your and you put your thumb in the direction of the current, then look at the curling of the fingers. The curling of the fingers will give you the direction of B, will give you the direction of B. The B's are directed like this way, right? If there was a current carrying wire, carrying a current like this, downwards, and if you took a loop like this, and then you curl your finger and you put your thumb, if this is your only thumb, some people have multiple thumbs, right? Yeah. If this is your only thumb, a normal thumb, and you place your thumb aligned with the current carrying wire, observe the curling of your fingers, right? Then the curling of the fingers would be like this, and you'll have all the B's along the tangent to the loop, which would be this way, because the curling of the fingers is like this. Yes or no? Right? In fact, so this was a very thin long wire. This was a very thin long wire, and we computed the magnetic field because of this thin, very long wire. At a distance r, it was mu naught I by 2 pi r, right? Now, suppose the wire is not very thin, is of finite width. Suppose the wire is of finite width. Width, and say it's a rectangular wire, it's a rectangular very long wire. This is the wire and is of width W, is of width W, and it carries a total amount of current I through this cross section upwards. Infinitely long, current carrying wire, not thin, but of a finite width W, right? And it carries a current like this. Okay. And at this point P, say at a distance small a from the nearer end of this wire, I want to be able to compute the magnetic field. At this point P, I want to be able to compute the magnetic field for this stretch of wire. Clear? Now what I do is, this wire then, I can break up into several thin wires. Say this is one thin wire. This is one thin wire. And this wire could be located from the point P at a distance x from P. At a distance x from P, I can locate this thin wire. And this thin wire, let's say, is of thickness, very small thickness, dx. I can compute the B at P because of this thin wire. And all the thin wires are from x equal to a to x equal to a plus w. And do you realize, for the point P, every thin wire is to the left of the point P, and therefore if it carries a current like this, then the magnetic field at P, this is my dl, these are my r's, so dl cross r would be into the plane of the board. So every thin wire will produce a field at P which would be into the plane of the board. So I would just need to compute, I would just need to add the dBs produced by all these thin wires at the point P, just like I add scalars, right? Now, the question then is, what's the magnetic field produced at P by this chosen thin wire, right? It's going to be mu naught times the current that it carries divided by 2 pi x into the plane of the board. Mu naught times the current that it carries divided by 2 pi x, right? And then I have to sum it up starting from x equal to a plus w to incorporate the impact of every thin wire that constitutes this finite width w, right? This length, it's infinitely long but has a finite width. The earlier one was infinitely long but was thin. This is an infinite number of thin wires but each being infinitely long. Clear? Now the only task ahead of us is to apportion a current to this thickness dx. The total current is I, which is uniformly spread over thickness width w. So the current that I want to associate with this di is going to be, well, the current per unit width is I by w. So the current apportioned to thickness dx would be this. That's going to be the current apportioned to this thin wire, right? Therefore, the magnetic field produced at P by this thin wire into the plane of the board, in this case for the figure shown, is going to be mu naught times the current di, which is I by w into dx, divided by 2 pi x, mu naught times the current, this is the current, divided by 2 pi x, and it's going to be into the plane of the board for the given diagram. That's the magnetic field produced by one thin wire. The total magnetic field produced at P is going to be sum of all of this, where x runs from a to a plus w. Which then gives us a value mu naught I divided by 2 pi w log a plus w divided by a. Yes or no? 1 by x is log x. That's a magnetic field produced at P by a finite width w of an infinitely long wire, right? Now, let's look at some other geometries. Now, Now let's look at a circular arc carrying current. All right. This is a circular arc P to Q and it carries a current I. And say this circular arc subtends at the center O an angle alpha. And say R is the radius of this circular arc. I want to be able to compute the magnetic field at O because of this current carrying circular wire. Current carrying circular wire. Right? Now what I do is, in principle then, between P and Q, I select these elements dl. Each dl would be along the tangent to the loop. Will be along the tangent to the loop. Each dl is along the tangent to the loop. For each dl, this is O, the center. I compute this length is r. And from this point to this point would be the position vector of O with respect to dl. Right? I do a calculation of the magnetic field at O. Do you realize that these are my R's from this point to O and these are my DLs? Every DL is perpendicular to R. Magnitude of each R would be the radius of the circle. For every DL along the loop, the magnitude of R would be the radius of the circle, and each DL will be perpendicular to R. Angle between DL and R would be 90 degrees, right? Not only that, this is O. Realize that dl cross r would be into the plane of the board, for this being the trajectory of the current. So each dl cross r would be into the plane of the board. Into the plane of the board. So all the dBs would be into the plane of the board. Therefore dBs could be added like scalars because they have the same direction, right? Which means now, let's say for this dl, the magnetic field produced at O is going to be mu naught by 4 pi I dl cross r would be simply dl into r. Why? Because dl and r are perpendicular to each other. dl into r divided by r cubed. Yes or no? dl into r into sine 90 degrees. Angle between dl and r is 90 degrees. dl cross r would be dl into r into sine 90 degrees divided by r cubed. And this dB is into the plane of the board. All that I need to do is, I need to carry out a scalar summation of all these dBs by taking dLs from P all the way to Q. Right? So which means now, the net B produced at the point at the center of the circular arc would be a scalar summation mu naught I by 4 pi r squared dl. This summation to be carried out from P to Q. All the dLs from P to Q would have to be included. I mean, don't look upon these P and Q as limits of integration. This is just to suggest to you that this summation has to be carried out from the point P to point Q. They're not like technically the limits of integration, right? So that's between you and me. That's the understanding. Okay. Now, mu naught I and R are constant, so this will scoop out. Then integral dl is what we will be left with. Integral dl would be the length of this arc. Yes or no? Integral dl would be the arc length PQ, which would be R alpha. Right? So then this becomes like a mu naught I by 4 pi r squared into R alpha. right? Which is like mu naught I by 2r into alpha by 2 pi. Yes or no? This r and this r, 1 r will get cancelled. So into alpha by 2 pi, that's the magnetic field produced at O. And since all the dBs were into the plane of the board, if this was the sense of the current, see, these were my dLs, these were my r's, so all the dl cross r's were into the plane of the board for this being the sense of the current. This B would be into the plane of the board, right? If the current were to be going this way, then the B at O would have been out of the plane of the board, right? Now, when this becomes a full circle, alpha becomes equal to 2 pi. If this becomes a full circle, this is the case where alpha is 2 pi. And if this was the direction of the current, which is like clockwise, as you can see, this is clockwise, then the magnetic field would be into the plane of the board and would be of magnitude. The B at O is going to be mu naught I divided by 2r. Mu naught I divided by 2r would be the magnetic field. In this case, it would be into the plane of the board. So if the current were to be circulating like this would be into the plane of the board, and we do this. This would mean the field is into the plane of the board. And if the current were to be circulating anti-clockwise like this, then the B at O would be out of the plane of the board. See, if this means into the plane of the board, this would mean out of the plane of the board. So it would be of magnitude mu naught I by 2r out of the plane of the board. So this is the convention. This would henceforth mean into the plane of the board. This would mean coming out of the plane of the board. That would be the convention that we would deploy. Now, again, a thumb rule, you don't want to do a dl cross r all the time. I do a dl cross r all the time though. Okay. And you take your right hand, curl your fingers in the sense of the current and observe your thumb. That will give you the direction of B at O. In this case, curl your fingers like this. It goes into the plane of the board and that gives you the direction of B. In this case, curl your fingers in the sense of I and it comes out. So B would be out of the plane of the board, right? But I'll tell you, fundamentally, I'm a strong subscriber of DL cross R's only, because if you learn too many left hand, right hand, left leg, right leg, thumb rules and leg rules, then sometimes it could be dangerous in an examination hall if you get very physical during a problem of magnetism, right? You would be reprimanded and it would leave the invigilator very suspicious of your activities. So by and large, DL cross R is a subtle movement, whereas, moving your hands up and down. I remember I was appearing for my HS exam, and it was in a place which was infested with people from across the cross section of West Bengal. People from very remote villages were also there to appear. That was a center, some Ashutosh college, and this gentleman who came from, very naive fellow, down to earth, trying to do things right, but he was doing this and doing this. It was Ampere's swimming rule for something. Hey, you don't swim around in an exam like this. The fellow was so strongly reprimanded because the invigilator doesn't understand physics, but he would take this very seriously. When you do this, when you do that, it will not be taken very lightly. So then he said, "Ki kocho?" Baje chele. He was chucked out for a while and then, was restored. Poor fellow felt so handicapped because without Ampere's swimming rule, he couldn't obtain some directions. So, too many left hand and right hand rules, and sometimes, when you have to use a right hand rule, but your right hand is busy with the pen, by mistake you use the left hand rule and you get all ulta pulta, right? So, a DL cross R is subtle, graceful and acceptable. So then, one way or the other, even if you want to use left hand, right right leg rules, make sure your movements are subtle and within limits of acceptability. That's all. Now, so coming back to this, the magnetic field produced at O by a circular arc is mu naught I by 2r into what proportion of alpha is with respect to 2 pi. Now, in case there were n closely wound turns of this loop, in case there were n closely wound turns of this loop, then the magnetic field at O, if there were n turns closely wound, then the magnetic field at O is going to become mu naught I by 2r into the number of turns that were closely wound, into number of turns that were closely wound, right? Now, suppose these n turns were not closely wound. In the sense, they were closely wound, but this thickness of these n turns become finite. In this case, if they are n very closely wound, that means the distance between the closest turn and the farthest turn is so negligible that the radius remains r only. Then mu naught I by 2r is going to work for computing the magnetic field at the center of this loop. However, you could have had a situation as follows. N turns this was O, the center of a loop. All right. This was a point at a distance small a from O. And these were closely wound loops, but they affected the total radius. The inner radius was small a and the outer radius was small b, say. Inner radius was small a and outer radius was small b. And say it was carrying a current I like this way. This kind of a structure is called a spiral. This kind of a structure is called a spiral, in which the radius varies from A to B, continuously varying radius from A to B. Okay, that's called a spiral. And there were, say, n turns of the spiral. Radially spread from r equal to A to r equal to B uniformly. In the radial direction, if you move, you would find n turns. You would find n turns, right? That means, if in the radial direction you moved, this was the radial direction from O, then in this direction, the number of turns per unit radial distance, would be n by b minus a. Yes or no? Yes. Right? Over a separation b minus a, there were n turns. So, number of turns per unit radial distance is going to be n by b minus a. That's the number of turns per unit radial distance, right? Now, for this loop carrying a current I, for this spiral carrying a current I want to be able to compute the magnetic field at O. One thing, for each of these loops, realize that this is the sense of the current, the magnetic field will be out of the plane of the board, right? So the net field at O is going to be out of the plane of the board. Now, what I do is, from O, I select a small thickness dx of this spiral. Say, I take this r and I select a small thickness, say dr of this spiral. Right? This is a small portion dr of the spiral that I have selected. This is practically like a circular wire carrying a current I, right? Then the magnetic field at O produced by this is going to be mu naught I divided by 2 pi r into the number of turns in this thickness, yes or no? The magnetic field at O produced by this thickness dr coming out of the plane of the board is going to be mu naught I by 2r, into number of turns over this dr, number of turns per unit radial distance is n by b minus a. Therefore, over this dr, the number of turns would be this much. Right? So that's going to be the magnetic field at O produced by this dr of the spiral, and it's going to come out of the plane of the board. For each of the drs, it's going to be out of the plane of the board. So the field at O is going to be out of the plane of the board. So the net field at O is going to be sum of all of this, where r runs from A all the way to B. That's the magnetic field at O coming out of the plane of the board if the current was this way. If the current was like this, it would go into the plane of the board. Yes or no? Now, which then boils down to the field at the center of the spiral of inner radius small a and outer radius small b is going to be mu naught I Ni. N is the total number of turns spread from r equal to a to r equal to b, divided by 2 into b minus a. 1 by r dr would be log r, so that's going to become log b by a. Yes or no? Now, suppose we had a circular arc in which different segments were carrying different amounts of current. Say, this was a circular wire, this was a point P, this was a point Q. This was the center of this circle, right? Points P and Q I connect to a battery of EMF EPSA, say. P and Q I connect to a battery of EMF EPSA. Say the minor arc PQ subtends an angle theta 1 at O, and the major arc subtends an angle theta 2, which is such that theta 1 plus theta 2 must be 2 pi. Right? There is a minor arc and there is a major arc subtending theta 1 and theta 2 at the center, and P and Q are connected to a battery of EMF EPSA. Now, if a current I flows through the battery, if a current I flows through the battery, then on arriving at P, it will have part of the current would be going along the upper arc, part of the current will flow through the lower arc, right? Say the current flowing through the lower arc is I1 and current flowing through the upper arc is I2. Yes or no? And the upper arc and the lower arc are in parallel. These two resistors are in parallel because they are connected across the same terminals P and Q, right? So they are in parallel. Now, notice that the magnetic field produced by the upper arc is going to be what? B, because of the upper arc, is of magnitude mu naught I2 divided by 2r, r being the radius of this circle, into theta 2 divided by 2 pi. And do you realize this is going to be into the plane of the board? This is going to be, see, curl your fingers this way along I2, the thumb points into the plane of the board. So this is going to be into produced by the lower arc. See, this is I2 mu naught I1 divided by 2r into theta 1 by 2 pi, right? And look at this current, it goes outwards because curl your fingers in the sense of the current, the thumb points out. So this would be out of the plane of the board. Yes or no? So the net B would be the algebraic sum of these. This is into, this is out. So the net field into would be this minus this. So the net field at O, which is into, is B because of the upper minus B because of the lower. They are in opposite directions, right? So that's going to be mu naught I1 mu naught I2 theta 2 I2 theta 2 minus I1 theta 1 divided by 4 pi r. Yes or no? Now, so far so good, right? Hey, if the upper loop had resistance R1, R1 is the resistance of upper loop. Upper loop, R2 is resistance of lower loop. Or rather, let me just do, because I've selected 2 for upward. So R2 is resistance of upper loop and say R1 is resistance of lower loop. Right? So can I say R1 into small r1 is I2 into small r2? Why? Because they are in parallel. The drop across this is the same as drop across this. Each will be equal to epsilon. So can I say I1 into small r1 is I2 into small r2? Yes or no? Potential drop from P to Q, whether you compute it like this or you compute it like this, it's going to be the same. So I1 into this resistance must be equal to I2 into this resistance. Hey, but the resistance of this will be proportional to this length and will therefore be proportional to theta. The resistance of this will be proportional to this theta. So can I replace these resistances by thetas? So can I say I1 theta 1 must be equal to I2 theta 2? Yes or no? Can I not say this? These resistances are proportional to these lengths, which in turn are proportional to these angles at the center. So can I say, can I replace these R1 and R2, the resistance of the upper and lower, by theta 2 and theta 1 respectively? So can I say I1 theta 1 is I2 theta 2? If I1 theta 1 is I2 theta 2, the field at the center will become 0. Field at the center will become 0. Right? Clear? Clear? So far so good, right? Physically also you can see why. Now, suppose there was a circular ring, and there was charge Q glued to this circular ring, uniformly glued to this circular ring. This is a circular ring, and there was charge glued to this circular ring. Charge Q glued to the circular ring. And at the center of this ring, this is the center of this ring, and this ring is given an angular velocity omega. Say the radius of this ring is r, and the ring is given an angular velocity omega. Now if this ring is given an angular velocity omega, then one could imagine an equivalent current flowing through this ring. The equivalent current that one could imagine flowing through the ring is going to be Q divided by the time period of rotation, which is 2 pi by omega. That's the equivalent current that you can associate with it. Q divided by the time it takes for a full revolution, which is 2 pi by omega, omega being the angular speed. This is the equivalent current associated with the ring. And if this is the equivalent current associated with the ring, the magnetic field produced at O, because of this current, is going to be mu naught times the equivalent current, which is Q by 2 pi by omega, divided by 2r. Mu naught times I is Q by 2 pi by omega divided by 2r. That's going to be the magnetic field produced by this arrangement. And the direction of the field would be into the plane of the board. Now, instead of charge being glued to a ring, let us imagine charge being glued to a circular disc uniformly and imparted a velocity omega, let's say, in one sense or the other, right? There is no current. I can imagine this to be an equivalent current. It's as if this charge Q, it undergoes a full revolution in a time equal to 2 pi by omega. Right? That means there is an equivalent current that you want to attach to this equivalent, which is Q divided by the time for a full revolution. Right? So equivalently, that would be imagined to be the rate of flow of charge in a very loosely speaking sense. Now suppose there was a disk. Say non-conducting. This ring was also non-conducting, so that the charge remains glued. This disk is also non-conducting, of radius r, and charge was uniformly available on this non-conducting disk. Right? There was a total amount of charge Q spread over pi r squared, uniformly spread over pi r squared. So this was the surface charge density available on this disk of radius r, right? And this disk was imparted a velocity omega. I now want to be able to compute the magnetic field at O because of this arrangement, right? What I could now do is, I could break this disk into several circular rings, right? This is one ring, O, radius small r and of thickness dr, right? Clear? And this ring has an angular velocity omega like this. This ring has an angular velocity omega like this, right? Now, the charge on this ring would be how much? Sigma, charge per unit area, into this area, 2 pi r dr. That's going to be the charge on this ring, right? Divided by the time it takes for a full revolution would be the equivalent current associated, total charge. This is the total charge on the shaded region, divided by 2 pi by omega. That's going to be the equivalent current that you want to associate with it, right? Now, mu naught times the current associated with it, divided by 2r, is going to be the magnetic field at O produced by this equivalent current. I hope you realize this. The charge per unit area on this disk is sigma by pi r squared. The chosen ring is of radius small r and of thickness dr, right? So the charge in the shaded region would be charge per unit area, sigma, into the area of the shaded portion. Area of the shaded portion is circumference 2 pi r into thickness dr. Now, and this charge is revolving at the rate of omega radians per second. So the equivalent current would be charge divided by 2 pi by omega. If this is the equivalent current, then mu naught times the equivalent current divided by 2r would be the magnetic field at O produced by this chosen ring, right? The net magnetic field at O then would be the sum of all of this, and realize that if this is the direction of omega, this is the direction of current, and the field would be into the plane of the board, right? So the net field at O would be sum of all of this, where r runs from 0 to capital R. If it was an annulus of radius small a to small b, then sigma would have become q divided by pi, say b squared minus a squared, and the limits of integration would be r equal to small a to b if it was an annulus instead of a full disk, right? So this then would be the magnetic field at O. In this case, it would be into the plane if omega is clockwise. If omega is anti-clockwise, this b would have been out of the plane of the board. That's going to be the b, yes or no? And then doing a very simple calculation on this, this integration would become mu naught sigma omega by 2. This r will also get cancelled, and then you simply have into r when you limit. Integral dr would be r runs from 0 to capital R. That's going to be the magnetic field at O. Clear? Now, let me look at yet another standard result. There is a current carrying circular loop. We have computed the field at the center of the loop, mu naught I by 2r, right? Now we would look at a point on the axis of this loop. Now we would look at a point on the axis of a circular ring carrying a current I, all right? So this is a circular ring of radius capital R. This is the axis of the ring. This is the center O of the ring. And say this ring carries a current I. At a point P of this ring, I want to be able to compute the magnetic field. this P is located at a distance x along the axis from the center of the ring. The location is x units from O along the axis, such is the location of the point P. I then wish to compute the magnetic field at P. I then wish to compute the magnetic field at P because of this circular. For a ring, for the center of the ring, x will become 0, a case that we have already arrived at. Okay. Now, again, objective very similar, very pretty much same blueprint, a little difference in algebra and trigonometry, but realize that what I would do is this current carrying wire, I'm going to break up into several DRs along the DLs along the circumference. For each DL, I'll compute the field at P and then do a vector or a scalar summation as is deemed fit for this situation. This is what I'm going to do in principle, right? And also notice one very simple fact, that if this was the ring, if this was the point P, then notice that this along with these would generate a cone. There would be a cone generated out of this, isn't it? And say if this angle is theta, this would be the slant height of the cone, small r, this is capital, this is x, and this would be r, capital R, the radius of the ring. Very clearly the slant height of the cone would be r square plus x squared, as you can see, right? So far so good, right? This would generate a cone with slant height small r. Every DL, with every DL, if you join the point P, it would be the slant height of the cone of radius or of length small r, right? Now, let me, so when I see the ring from the top, I see a circle, but when I see it from side, I'll see something like this. If I see the ring from the side this way, then what I see of the ring is this thin ring. This is what I see of the ring. The center O would have been somewhere here. This would be the axis. Say this point is P, this point is Q. P and Q are extremities of the diameter, right? Oh, let me call this M and N because I've selected this point as P. So let me call this M and N. Now, this is M, this is N. So if you see from the side, you see this thickness. When you see from the top, you see this, isn't it? Right? Now, the DL at M is jutting into you, isn't it? Is coming towards you. Every DL will be along the tangent, would be along the tangent to the ring. So the DL at M would be perpendicular to the board. The DL at M would be perpendicular to the board and will be coming towards you because the current is coming like this and is tangentially flowing through the circumference, right? So it's going to be jutting out. Clear? Do you all understand? So the DL at M is going to be like this, right? This would be the slant height of the cone, right? This would be the slant height of the cone. Clear? And for this DL, this would be the vector R leading to the point P. Yes or no? For this DL coming towards you, then from this point to this point would be the vector R, which is used in Biot-Savart, DL cross R vector, right? It's towards R. And realize that DL and R are perpendicular for every DL. DL and R are perpendicular for every DL. DL like this. This is in the plane of the board. So DL cross R would be simply DL into R into sine 90 degrees, right? So the magnetic field produced at P by this DL jutting towards you at M the magnitude of the magnetic field produced at P because of this dl jutting towards you is going to be mu naught by 4 pi I, the current, dl cross r. dl into r into sine 90 degrees. Therefore, that will be simply dl into r divided by r cubed. That's the magnitude of the field at P. Clear? Now, realize that if this is dl, this is r, dl coming towards you, this is coming towards you, this is r leading to the point P, right? So, dl cross r will always be perpendicular to both dl and r, will be perpendicular to the plane of dl and r, right? So, dl is like this, r is like this. Do you realize that dl cross r would be like this? This is dl, this is r. So, right hand screw rule, perpendicular to dl as well as r would be this. Yes or no? This is dl, this is dl, this is r. dl cross r goes this way, right? So, dl cross r would be like this. If dl comes out of the plane, if dl were to be going into the plane, then it would, dl cross r would have been this way, right? This is dl, this is r, so dl cross r is like this, perpendicular to both dl and r, right? So this would also be the direction of db. This would also be the direction of db, right? Now what I could do is db I could just shift to p. So my db at p, this is the point M, this is the point P, the dB is like this at the point M, and in the direction of dl cross r I shift this to this point perpendicular to this. This would be the dB, yes or no? Whose magnitude is this? Isn't it? So my dB is of magnitude dB and is shifted to the point P like this, right? Say this angle that dB makes with the vertical is theta. This is the angle that dB makes with the vertical. This is theta, this is 90 minus theta, this is theta. So this will be theta, right? I hope all of you understand this. This is theta, this is 90 minus theta, this will be theta, alternate angles, this will be theta, right? Now, do you realize all the dBs produced by various elements make an angle theta with the vertical, so they are all in different directions. They constitute, all these dBs constitute an inverted cone with vertex here, yes or no? All these dBs constitute an inverted cone with vertex at P, yes or no? Do you all realize that? dBs are in different directions, so I can't say the net B at P would be sum of all these dBs. That's going to be gross, right? So what we'll have to do is, we will have to resolve dBs horizontally and vertically, each dB, right? So the dB is resolved as dB cos theta and dB sin theta. Now also notice that if for the point M my dB is like this, making an angle theta this way, then I want you to independently evaluate that dB for the point N would be theta like this, right? And the horizontal component of dBs, that is dB sin thetas, will cancel off for diametrically opposite points. So all the dB sin theta would add up to 0. That means we only have the task of taking care of A summation of dB cos thetas. All dB cos thetas are vertical. The net field at P therefore would be vertical along the axis, and they can be added like scalars. Right? So the only task ahead of us is to be able to add dB cos thetas. Sum of all the dB cos thetas at P is going to be along the axis and upwards for the given figure. Right? Now, the net field at P is going to be sum of all the dB cos thetas, where this summation is carried out along the, for all points of the ring. All elements dl of the ring would have to be chosen while carrying out this summation. Right? And do you realize that this theta will remain the same for all elements? Slant height of the cone making the same angle with the base of the cone, right? This theta is a constant therefore, and that makes life very simple. So the net B is going to be mu naught I by 4 pi r squared, right? Mu naught I by 4 pi r squared cos theta into dl, right? This cos theta and this dl, this computation to be made for all dl's of the ring. Again, this small r is the same, slant height of the cone is the same for all dl's. So mu naught I by 4 pi r squared cos theta, everything comes out, and integral dl would be the circumference of the ring, which would be 2 pi into capital R. 2 pi into capital R. Yes or no? Right? So this is like mu naught I by 4 pi r squared coming out. Cos theta. What is cos theta? This is capital R divided by small r. Yes or no? Capital R divided by small r. That's cos theta. Capital R divided by small r. So capital R divided by small r. So this will become r cubed into integral dl, which would be the circumference 2 pi r. Which then becomes mu naught I r squared by 2 into r cube, where small r squared from Pythagoras is capital R squared plus this was x, this was x, this was r plus x squared. So plugging in small r from this will give you mu naught I r squared by 2 r squared plus x squared to power 3 by 2. If the current was like this, then you would notice the thumb going up. If the current was in the opposite direction, the thumb would point down. Curl your fingers in the sense of the current and observe your thumb using your right hand. That will give you the direction of B. Okay. Now, if this was a ring with n turns, n closely wound turns, then all that you would have is the field would become n times. If there were n closely wound turns, mu naught I r squared divided by 2 r squared plus x squared to power 3 by 2. That's going to be the field at P. Yes or no? All's good. So if there were n turns, you just multiply it by n. Clear? So far so good. Now, can I wipe this off? Sometimes what we encounter is the following. sometimes we encounter the following. There could be a cylinder, and several turns of a coil wound around the cylinder. Several turns of a coil, closely wound coils turned around the cylinder. Say a current I enters. This cylinder is non-conducting. Non-conducting cylinder, and these are conducting coils carrying current I. This is the axis of the cylinder. R is the radius of the cylinder. And say, number of turns per unit length, number of turns of this coil per unit length that you encounter are small n. Small n is number of turns of this coil wound around the cylinder. Per unit length wound around the cylinder. That means if you take unit length, then the number of turns of this coil that you would encounter would be small n, right? And for this arrangement, on the axis of this cylinder, say, this cylinder could be hollow or solid, right? Does not matter. At this point P, located somewhere on the cylinder, I want to calculate the magnetic field because of this coiled arrangement. Because of this coiled arrangement, I want to be able to calculate the magnetic field at some point on the axis of the cylinder, right? I locate this point P by some means first. I would have to locate this point P by some means. What I do is, can I wipe this off? So, this is the cylinder. To avoid clutter, I am avoiding to draw the coils, but you understand there is a coil that winds around the cylinder, and number of turns per unit length that you would find would be small n, say. Okay. This is the axis of the cylinder. Hey, if this was a solid cylinder and P was on the axis, then that solid cylinder material would have permeability, relative permeability mu r. Then what you would have to do is you would have to multiply that mu naught by mu r. If it was a hollow cylinder and this point P was in air, then mu naught will suffice, right? That's only. So let me take it as a hollow cylinder and the point P as in air. So I'll just use permeability mu naught, right? Now, this point P located with the help of two angles, say theta runs from theta 1 to theta 2. This is theta 1 and say this is theta 2 from. Such is how I locate the point P. Such is how I locate the point P. And say in terms of lengths, say this length is L1, say this length is L1 and this length is L2. very clearly cos theta 1, as you can see, even they are all connected, would be L1, this is the radius r, so this would be root L1 squared plus r squared. So cos theta 1 would be L1 divided by root L1 squared plus r squared, right? This is pi minus theta 2. This is pi minus theta 2. So cos pi minus theta 2, which is minus cos theta 2, is going to be this length L2 divided by this length. This is r. So this length would be root L2 squared plus r squared. Right? Yes or no? Now, what I do is, point P on the axis, right? At a distance x from the axis, I select this coil. At a distance x from the point P along the axis, I select this coil, right? And of thickness dx. So this is a current carrying wire, dx is a current carrying wire, and P is a point on the axis of this current carrying loop. Let me compute the magnetic field at P because of this dx, for which I will have to deploy the previous result, mu naught into ni r squared by 2 r squared plus x squared to power 3 by 2. The radius of this ring is going to be capital R, right? The magnetic field at P because of this dx, a circular ring. This is a point on the axis of the circular ring which carries a current I, say current I. The magnetic field is going to be mu naught times I r squared by 2 r squared plus x squared to power 3 by 2 into the number of turns in this. Number of turns per unit length is n. So number of turns over dx is going to be n into dx. So into number of turns over this dx is going to be n into dx. That's the magnetic field at P produced by this. Yes or no? The total magnetic field produced at P is going to be sum of all of this, where x runs from minus L2 to plus L1. X runs from minus L2 to plus L1. Yes or no? That's going to be the magnetic field at the point P. When you integrate and write this L1, eventually you get in terms of x, this is an easy to integrate function, and then you write in terms of L1, L2, you can put it all in terms of cos theta 1, cos theta 2. Let me tell you the final result that you will encounter. You would encounter mu naught ni by 2 cos theta 1 minus cos theta 2 is what you would encounter. Mu naught ni, where n is the number of turns per unit length. If it was a solid cylinder, then this mu naught would be into mu r, which is the relative permeability. Mu r is the relative permeability of the material of the solid cylinder, right? Otherwise, it's going to be this, right? Now, this arrangement coiled around a cylinder is essentially what's called a solenoid. This is called a solenoid. This arrangement is called a solenoid. This arrangement is referred to as a solenoid. And an ideal solenoid would be one in which L, the length of total length L, is much larger compared to the radius R. And if P is the midpoint, if P is the midpoint, then, and if L is very large, and if P is the midpoint, theta 1 would be 0 and theta 2 would be pi. Isn't it? If L is very large and P is the midpoint, then theta 1 would be 0 and theta 2 would be pi. Right? And then the B at P, B at such a point, almost the center of an ideal solenoid is going to be, this would be 1, this would be minus 1. So this will become 2, 1 minus 1. So 2, which is like mu naught Ni at the center of the solenoid, ideal solenoid, right? In fact, you would want to check for yourself almost towards the end of the solenoid, plug in suitable values of theta 1 and theta 2. So magnetic field versus X, this being the center of the solenoid, close to the center, this remains, B remains mu naught Ni. And then towards the end, it will become mu naught Ni by 2. This is the end. Mu naught Ni by 2 is what this will become towards the end of an ideal solenoid. This is roughly the variation of V of B versus X from the center of an ideal solenoid. At the center, it's important to know it's going to be mu naught Ni. N is not the total number of turns, is the number of turns per unit length. I is the current. Towards the end, it will become mu naught Ni by 2. You want to check that by suitably plugging in theta 1 and theta 2. One of them will be 0, the other one would be 90 degrees. At the ends, one of the thetas would be 0, the other one would be 90 degrees. So that will give you mu naught Ni by 2 at the extremities, at the X. So this is roughly the variation of, at close to the center, it will remain practically mu naught Ni by 2 and then gradually dip to mu naught Ni by 2 towards the end of an ideal solenoid. Right? And if it was a solid solenoid, then this mu naught would be replaced by mu naught into mu r, where mu r would be the permeability of the material of which the solenoid is made. Clear? Now, just like we had Gauss's law in electrostatics, where electric fields could be computed for symmetric situations with greater amount of ease, where we said we took a closed surface and we said E dot ds, integral E dot ds is charge enclosed by epsilon naught. Symmetry could help E to scoop out, E into total surface area, charge enclosed by epsilon naught, and we could compute E for symmetric situations. An equivalent of the same in magnetism exists, and which is about, say, there could be several current carrying wires in a certain region. Say this carries a current I1, This carries a current I2. This carries a current I3. And each of these current carrying wires will produce their own magnetic fields. So the region would be a region of variable magnetic fields surrounding these current carrying wires, right? Now, I could have taken a loop, any loop surrounding these current carrying wires, any loop enclosing the wires. This is any loop that encloses the wires. Any closed loop enclosing the wires. And at every point of this loop, there is going to be a magnetic field. Because of the combination of these wires, there is going to be a magnetic field at every point of the loop. Now, every point of the loop could be traversed either this way or this way. The loop could be traversed in any manner. Suppose I traverse the loop like this. This is any arbitrary loop that I am imagining enclosing these wires, right? And I could traverse the loop in any sense, say. Okay. Then if I circulate the loop in this sense, then for every point, the dl associated with the loop, this is not a current carrying wire, by the way. This is not just a imaginary loop, just an imaginary loop. And with every point p of this loop, the direction of the loop is going to be given by dl, which is along the tangent, which would be along the tangent at that point, right? And the b at every point, let's say, is b. At different points, b will be a function of where the dl is selected, right? So for every p, for every dl that constitutes this loop, I could do a b dot dl. See, if I were to be circulating the loop like this, then the dls would be this way. Tangential, but would be oppositely directed, right? But one way or the other, the b dot dls could be computed for every p of this loop. For every p, there is going to be a b and there is going to be a dl. So I could do a b dot dl. I could do a b dot dl for every point of this loop, and a b dot dl will be a scalar, would be a number. The b dot dls would be a number. Sometimes it's going to be positive, sometimes it's going to be negative, sometimes it could also be 0, right? So the b dot dls are computed and they are added for the loop. That means if this b dot dl is computed and added for the loop, then you put this, it would mean there is a full loop. If you do this, means this b dot dl is for the entire loop. Right? And this loop is what's called an Amperian loop. That surface was called a Gaussian surface. This loop is called an Amperian loop. For this Amperian loop, I do a b dot dl, and that from what's called Ampere's circuital law. Is going to be mu naught times I net enclosed. Now, there is something about the sign of these eyes. Some of these eyes will be positive, some of these eyes would be negative. Very clearly, I1 and I2 would be of opposite signs. I1 and I3 would be of the same sign. Now, the way to determine the sign of these will depend on how you are circulating the loop. What you do is, if you are circulating the loop like this, for example, as shown in the figure, curl your fingers along the loop, curl your fingers of the right hand along the loop. Then all currents in the direction of the thumb would be positive and opposite would be negative. So I'm circulating the loop like this, given by curling of my fingers. So currents in this sense would be positive and currents in this sense would be negative. So this would then turn out to be mu naught times I enclosed, which is I1 plus I3 minus I2. Right, I1 and I3 are both along the thumb and I2 is opposite to the thumb. Right? If I had selected a loop here, then integral B dot dl for this loop would have been 0. For this loop would have been 0 because there is no current enclosed. All the current carrying wires are outside this loop. Now, integral B dot dl equal to 0 doesn't mean that B is 0. Doesn't mean that the B at these points will be 0. It just means that summation of B dot dls. You do a B, you find a B here, a dot dl, a B here, a dot dl for every point. That integral, this is called a line integral. This is called a line integral will be 0. That will not mean that B is 0. However, if from symmetry one could figure out that the B is the same at every point and along the DL, then B would be 0, which we'll see in a little while from now. But so far so good, right? All of you understand this. This is Ampere's circuital law to be deployed in situations related to symmetry. In situations related to symmetry. Does not matter. They are all at an angle. They are not piercing perpendicularly the loop. It will not make any difference. Integral B dot dl, B will change at different points, true. If you change the orientation of this, say you make it like this, right? True, B at every point of this loop will change, commensurate, but integral B dot dl will remain mu naught times I enclosed. That it will not make any difference. That's Ampere's circuital law, right? Now, see, suppose there was an infinite straight wire, infinitely long straight wire carrying a current I. Infinitely long straight wire carrying a current I. I imagine an Amperian loop of radius R. I imagine an Amperian loop of radius R. This is the center of the loop lying on this straight wire. Now, one thing for sure, the DL cross R at this point would be into the plane. At every point, the DL cross R would be along the tangent to the loop. So, all the B's would be, first of all, from symmetry, the magnitude of B would be the same at every point because you can't distinguish between this point and this point. The wire treats all these points on the loop the same way. So the magnitude of B would be the same and the direction of B would all be along the tangent. That means all the B's would be along the DLs, yes or no? All the B's would be along the DLs. If B is along the tangent, the DL is also along the tangent, yes or no? So at every DL, the B dot DL will simply be B into DL. B into DL, that means integral B dot DL for every DL is simply going to be B into DL, because angle between B and DL is the same. B is along the tangent, DLs are also along the tangent, right? And I'm circulating the loop this way, right? So B dot DL, that must be mu naught times I enclosed. Since B is the same for all dLs in magnitude, it will scoop out. So B into integral dl would be the circumference of this loop, which is 2 pi r. That's going to be mu naught times I enclosed. So B then, as you would expect, and as computed earlier using integration, would be mu naught I by 2 pi r. Right? Suppose there was an infinite sheet of current. Can you bring your notebook here? Show it this way. You know, horizontally. Right? So this is a sheet, and say it's very long. Or rather than more than being long, it's wide, say. Wide. Okay? This way. And there is current that enters the sheet. Current. And the current per unit length of the sheet says some K. Okay? And I want to be able to compute the magnetic field produced by this sheet, you know, which entertains a total current I coming into this cross section. This is a thin cross section, and it entertains a current I coming into this cross section, and the current per unit length of the sheet flowing this way is, say, some K. Okay. I now want to be able to compute the magnetic field at a certain point close to this infinite sheet. All right, that is what we want to be able to do. So, looking at the end of the sheet, infinite sheet, carrying current K per unit width of the sheet. See, this is the sheet, and say current comes out of the plane of the board. This current is, say, coming towards you. These are all current coming out, right? This is a point P. What I do is, I could break it up into small elements carrying current this way, right? And I could sum it up. Or what I could do is realize that if I took an element dl here, right, in which current is coming out, at a certain distance from this line, say this is the central line, okay, at a certain distance, this was an element of width dl. That means the current associated with this element is going to be K into dl is going to be the current associated with this element, right? Then my dl is like this, r is like this, right? So dl cross r would be like this. This is my dl going upwards. This is my r going towards P. Then dl cross r would be like this, perpendicular to dl and r. Yes or no? Right? So at P, the magnetic field produced by this is going to be, say, dB like this. Right? dl like this, r like this. So dl cross r from cross product would be like this, perpendicular to both dl and r. Now, if I looked at a symmetric element dl on the other side of this line, on this side. Now, realize that dl is like this, r is like this, right? So, if this is dl and this is r, then the direction of db is going to be given by dl cross r, which is like this. Yes or no? It's going to be dl cross r like this. That means perpendicular to this, this would be my dl cross r, this would be my db. Right? And these db's for symmetric element would be such that the vertical components of db's will cancel off. The net would be a b in this direction, the net b would be in this direction, db and db would be parallel to the sheet. Would be parallel to the sheet, yes or no? So for points p very close, the b's would be all parallel to the sheet. And whether you take a point P here or you take a point P here, because of the infinite character of the sheet, B will remain practically the same. Right? I want to be able to calculate B very close to this infinite sheet of current, carrying current per unit length K into the per unit width K per unit width. This is the width dl of the sheet. So K into dl would be the current associated with this. Clear? Now, I'm going to deploy Ampere's circuit law towards this computation, right? What we do is, I take a loop like this, and all the currents are going into. I take a loop like this, say of length L. Let me take a loop of say width L, right? And I circulate the loop this way. This is my loop, RS. My B's at every point would be of the same magnitude B because of the infinite nature and would be leftwards. It's going to be leftwards at every point. All right. Above, it's going to be in this direction. Below, if I go like this, then B's would be like this. Because all the dB's would change direction if you go below, and you would find that the B's would be this way, below this. Right? Now, if I do a B dot dl from P, I circulate the loop this way. B into L, B dot dl for this portion is going to be B into L. Now, if I go from Q to R, my B's are like this, my dl's are like this, so B dot dl will be 0 for this. Then I go from R to S, my dl's are like this, because I'm circulating the loop this way, the B's are like this. So B into L. Then I go from S to P, my B's are like this, and my dl's are like this. So B dot dl will be 0. And that must be equal to mu naught times the current enclosed here. Current per unit width is K. So current over a length L is going to be K into L. So that's going to be mu naught times the current KL. So the B then turns out to be mu naught times K by 2. Mu naught K by 2. This is my Amperian loop. Right? Let me look at some more situations. These are all regulation results which you got to recall as and when required. Now, notice, suppose I have a hollow cylinder of radius r, infinitely long hollow cylinder means infinitely long cylinder of radius r, and it's carrying current longitudinally along its surface. It's carrying a current I longitudinally along its curved surface, parallel to its length, right? That's the current it carries along its length. And so on and so forth, right? Along the surface, curved surface, it's carrying a current longitudinally. And say the total current that it carries is I. Suppose I select a point P inside this at a distance r. I select a point at a distance r from the axis of the cylinder, right? Then this point P, I can imagine an Amperian loop of radius r. From symmetry, can I say that at all points of this loop, B will be the same? From symmetry, there is no difference between one point and another of this interior loop. Not only that, if there is a B, then each of the B's will also be along the tangent to the loop, again from symmetry, right? So then, integral B dot dl for this interior loop for r less than capital R, for any P at a distance small r less than capital R, is going to be B dot dl. That's going to be mu naught times I enclosed. I enclosed for this inner loop is going to be always 0. And B is a constant. Dot dl will be into dl, because B and dl from symmetry would be in the same sense. That is 0. B comes out, same for all dl, and that will cause B to be 0 inside. For any point inside this hollow cylinder, magnetic field is going to be 0, right? That is for small r less than capital R, right? Suppose we had small r points on or outside, small r greater than or equal to capital R, small r greater than or equal to capital R, right? This is the axis, and I select a point P outside the cylinder, right? Again from symmetry, B would be the same at every point and would be along the tangent to the loop, Amperian loop that I've selected, right? So integral B dot dl is going to be B into dl. B will come out. Integral dl will be the circumference of this loop. So B at every point here is going to be B into 2 pi r. That's going to be the line integral for this loop, B into 2 pi r. And that must be mu naught times the total current I enclosed. So on or outside the loop, it goes as 1 by r. Mu naught I divided by 2 pi small r. So it falls as 1 by r, which means now the variation of B versus small r starting from the center of, starting from the axis means the center, from the center to R, it is 0. And then from capital R onwards, B falls as R. This is the variation of B versus R for a hollow cylinder. Inside the cylinder it's 0. Then from the surface, outside it falls as 1 by R. This B into small r is a constant for points outside, and this part is going to be a rectangular hyperbola. Like P into V equal to constant is a rectangular hyperbola, B into small r equal to constant will also be a rectangular hyperbola. So this is going to be a rectangular hyperbola. Right? Now instead of a hollow cylinder, let me take a solid cylinder. Solid cylinder in the sense, you know, a solid current uniformly distributed along the cross section. Current uniformly distributed along the cross section pi r square of the cylinder. Again infinitely long. Okay. So that was current superficially distributed. This would be current that would be distributed in a cross section, uniformly distributed over a cross section. That means solid cylinder a total amount of current I that grows through a cross section pi r squared. So we define what's called current density J. J as I divided by pi r squared, current per unit cross section. Current density, and this current density also has a direction which would be like this. So this is the current density vector. This is the current density vector J, whose magnitude is this, and the direction is the same as I. Okay. Now, so that's uniformly distributed in the volume, right, through every cross section. Now if I take a point P inside at a distance small r, if I take a point P, this is my Amperian loop that I imagine for small r less than capital R, for points P inside the loop. Right? Again from symmetry, B would be the same at every point of this loop and would be along the tangent to this loop from symmetry. So integral B dot dl is going to be B into 2 pi small r. The B dot dl for this loop selected, Amperian loop selected inside, and that must be equal to mu naught times the current enclosed over small r, right? So that's going to be current per unit cross section pi r squared, which is J, into the cross section associated with it, pi r squared. No, see, I mean, it is as if I'm not talking of, when I talk of a cylinder, I'm not necessarily saying you can take mu r equal to 1 depending on, like I said, in every case I'll derive only for mu naught, but if they specify that, you know, it's mu r relative permeability is there, then you take mu r, but I'll derive only for mu naught. So if in a given problem they say, well, it's a solid cylinder of permeability mu r, then you multiply by mu r wherever required. Okay. So So then, very clearly, B would then become, see, this pi will get cancelled. B would then become mu naught I divided by 2 pi r squared into r, isn't it? This 2 pi r squared into r. Therefore, B inside varies linearly with r, right? Yes or no? B inside the cylinder varies linearly with r, given by this. Now, for r greater than or equal to capital R, this is the cylinder. Carrying a total current I through its cross section. I imagine an Amperian loop like this. This is a point P. The center O. This is R. Greater than or equal to capital R. So then for this case, again B from symmetry would be along the tangent. B dot dl would be B into 2 pi r. R is the radius of this Amperian loop. So B into 2 pi r would be the line integral B dot dl, and that must be equal to mu naught times the total current enclosed will simply be I. No matter what small r you take, this will simply be I. For points outside, this is for points outside. Clear? So then B goes like mu naught I divided by 2 pi r, which is like an infinitely long current carrying wire, right? For points outside, it behaves like a thin long wire, right? And therefore, if you have to trace the graph, then from the axis, this is a point on the axis, B versus distance from the axis. Inside the cylinder, it will go linearly with R. On the axis, it will be 0. Small r equal to 0 on the axis. The magnetic field will be 0. Then, at small r equal to capital R onwards, it will dip as 1 by r. This is how it happens. And do you realize at small r equal to r, it is continuous this time? Because see, small r coming closer and closer to capital R from the inside is mu naught I by 2 pi r. Small r coming in closer and closer to capital R from the outside is also mu naught I by 2 pi r. Therefore, B is continuous on the surface. So it goes this way. That's why. But it is not differentiable. It is not differentiable at. Right? So, in the previous session, what we looked at is essentially computation of B for various geometries, various situations, common stuff. Okay? And now we would get on to force experienced by a charge exposed to a magnetic field. Okay? So if there is a charge Q and it has a velocity v exposed to a magnetic field B, then like I told you at the very onset, the force experienced by this charge is going to be Q into V cross B. That's going to be the force experienced by this charge, Q into V cross B. Also, like I told you, so this is the magnetic force. And if Q is positive, the direction of F and the direction of V cross B will be the same. In this case, V cross B is into the plane of the board, for example. If Q is negative, the direction of F and direction of V cross B would be opposite. Also notice that F is perpendicular to the plane of V and B, perpendicular to both V and B. So F dot V is 0. F dot V is 0. This is the magnetic force. That means the magnetic forces do no work, are no work forces. Therefore, they cannot change the kinetic energy of a charged particle. They can change the direction of velocity, because with this force, this force is non-zero, right? This force F is non-zero, it's perpendicular to V. It can change the direction of V but cannot change the magnitude of V, right? So, power associated with a magnetic force is 0, or the work done by a magnetic force must be 0. It therefore cannot change the kinetic energy of a system, right? Say there is a charged particle Q at the origin. There is a charged particle Q at the origin. And it is subject to a magnetic field B. Say Bx I cap plus By j cap plus Bz k cap. This is a magnetic field B associated with a certain region where Bx, By, Bz all would be functions of x, y, z, variable magnetic field, right? And it is exposed to an electric field E, which is say E naught. E naught is a constant, k cap. And this particle starts from rest. This particle starts from rest, and in a complicated manner, after a while, it moves to a point P with coordinates x, y, z. I now want to find, let's say the mass of this charge is m. I want to find the speed of the charge when it reaches a point P. I want to find the speed of the charge when it reaches the point B, P. Now, I can apply work energy theorem to this. I could apply work energy theorem to this. Work done by B plus work done by E must be change in kinetic energy, right? That's work energy theorem. Now, work done by B will be 0 always. Work done by the forces of the magnetic field will always be 0. It's a no work field, right? Now, the work done by E, forces of the electric field, is going to be, okay, where no matter what its trajectory is, if it has to go from 0, 0, 0 to x, y, z, the only force that it experiences is in the z direction, which is q e naught, is the force because of the electric field in the z direction. And what's the displacement in the z direction? Z. So that's the work done by the electric field, yes or no? Yes. And this plus this must account for change of kinetic energy. So half mv squared must be q e naught z, must be q e naught z. That's change of kinetic energy. Clear? So you can compute the speed. It starts from rest and it develops a speed v. So change in kinetic energy is half mv squared. That must be work done by the magnetic field, which is 0, and work done by the electric field, which is q e naught z. Right? Clear? Now, see, if a charge Q is exposed to a magnetic field alone, is at the mercy of a magnetic field alone, then its speed v will not change with time. The direction of velocity will change, but the magnitude of the velocity will not change time, because magnetic fields are incapable of changing the kinetic energy because they are no work fields. So this V squared, which is square of the x component plus square of the y component plus square of the z component, must remain constant. Must remain equal to V squared, a constant. Now, it is possible that all three components change, right? All of Vx, Vy could change. Could change. Or only two change. But you can't have only one changing. Because if one changes, then this whole thing will change. So two or all of them must change if it's exposed to a magnetic field. Clear? Now, if a charge Q enters a magnetic field B with a velocity V, then there are various possibilities. One, say this is the velocity V and V and B are parallel to each other, parallel or anti-parallel. If they are parallel, angle between them would be 0. If they are anti-parallel, it's going to be pi. So parallel or anti-parallel, very clearly V cross B will be 0. So Q into V cross B will be 0, right? That means the magnetic force acting will be 0. That means the acceleration of the particle will be 0. That means V will remain constant. Therefore, the particle will go undeflected, undeviated through a magnetic field, through a region of a magnetic field, if it enters the field with a velocity parallel or anti-parallel with the field, right? It will not even know of the existence of the field. Why? Because the force because of the field is 0, so it will not even know that there is a magnetic field. It will know of the magnetic field only if it can interact with the magnetic field in terms of experiencing a force because of the magnetic field. Otherwise, it would not even know of that. How about it? Right? So it will move with a constant velocity, neither the direction nor the magnitude will change. It will move along a straight line parallel to B. Clear? Suppose there is a region of magnetic field, uniform magnetic field, say going into the plane of the board. These are magnetic field lines going into the plane of the board. B going into the plane of the board, uniform magnetic field. This is a region. And charge Q enters this region with V perpendicular to B. With V perpendicular to B. Charge Q enters this region with V perpendicular to B. Right? That means if B is like this, let's say the charge Q enters with a velocity V, whose magnitude is V perpendicular. B is going into. B into the plane of the board and V like this. V like this. Right? So then the particle experiences a force, this charge Q, mass M, will experience a force of magnitude Q into V cross B, which would be V into B into sine 90 degrees. That's the magnitude of the force that it experiences. And this force F, realize, is Q into V cross B, is perpendicular to V. Right? So it will only change the direction of V. It will not change the magnitude of V. So while this particle undergoes some kind of a trajectory, its speed will remain the same, but the direction of the velocity will constantly change. And if f always remains perpendicular to v, that means the trajectory associated must be circular. Circular trajectory, if f is always perpendicular to v. See, if a particle is thrown in a uniform gravitational field with a velocity v naught like this and g like this, right? In this case, force is perpendicular to v only at the initial instant of time, not at all instants. So the trajectory is parabolic, because force and v are perpendicular only at time t equal to 0, right? But in this case, force is always perpendicular to v. Force will always be perpendicular to v if this force behaves like a centripetal force, if the path executed is circular, if the trajectory is circular, and this f provides a required centripetal force to execute a circular trajectory. The direction in which this force acts would help us locate the center of the circle, because f will always pass through the center of the circle, the centripetal force. Yes or no? Now in this case, v is like this and b is into the plane of the board. So v cross b would be in that direction. This is v, and b is like this. So v cross b would be in this direction, in that direction. So the center of the circle will lie somewhere there, right? So the particle executes a circular trajectory of this kind. The particle executes a circular trajectory of this kind. Yes or no? With the center of the circle being somewhere here. The center of the circle being somewhere here. And of radius r. This is the direction of f. The centripetal force directed towards this. Right? Now, the speed v will remain same, right? The centripetal force, as you can see, is qvb and must be equal to mv squared divided by the radius r of the circle, right? So that gives me the radius of the circular trajectory as mv by qb, as the radius of the circular trajectory, right? Yes or no? And v by r will give me omega, angular speed of this circular motion. Omega is v by r, yes or no? Angular velocity, and v by r, as you can see, is qb by m. So omega, the angular speed, is going to be qb by m, right? And time period of motion, time taken to complete a full circle, is going to be 2 pi by omega, which is 2 pi m by qb. Right? Now, the important thing to understand here is that if v is perpendicular to b, then the trajectory would be circular, right? And the plane of this circle will always be intercepted by the b lines. The b lines are going into the plane, would be intercepted by the b lines normally, perpendicularly. The b lines would always intersect the plane of the circle normally, for which it is causing a circular trajectory. That is important to understand, right? Now, so far so good, right? So this is what transpires if a particle enters the region of a magnetic field perpendicular to B, then it will execute a circular trajectory. The plane of the circle would be intercepted by the B lines normally or perpendicularly, right? The radius of the circle is mv by qb, omega angular velocity is qb by m, and so on and so forth, right? Now, suppose a particle, so particle enters, charged particle enters region of a magnetic field inclined at an angle theta. Clear? That means this is the velocity v of the particle, and say this is the direction of the magnetic field, and the angle between v and b is theta. This is the point O where it enters. Now this v could have been resolved perpendicular to b and axially, which is parallel to b, right? So this v could have been resolved as v cos theta, v sin theta as the perpendicular component, and v cos theta as the parallel component. V cos theta and v sin theta, perpendicular and parallel components. V cos theta is also called the axial component. Component parallel to b is the axial component. So v perpendicular, like I said, is v sin theta. This is the direction of the magnetic field, and v parallel is v cos theta. Right? Now, what would be the level of interaction between v cos theta and b? 0, because they are parallel. So no matter what the trajectory is, there is no interaction between this component and this component. Therefore v cos theta will not change with time, because the force owing to v cos theta is 0, right? Now look at this v perpendicular v sin theta. V sin theta and b are perpendicular to each other. They connive to produce a circular trajectory. The circular trajectory would be such that this b lines would be intercepted by that circular trajectory perpendicularly, yes or no? Right? So v sin theta all by itself, suppose this was the x direction, right? Then the plane of the circle will be the yz plane, because the yz plane is intercepted by the b lines normally, right? So say this was the x direction, y direction, z direction, right? B is in the x direction, then the plane of the circle will be the yz plane. The plane of the circle caused by a connivance between v perpendicular and b would be the yz plane. Yes or no? Right? Now, if v cos theta was not present, it would be purely circular motion in the yz plane. Right? If v sin theta was not present, it would have been pure axial motion along the b direction. Right? Now if you superimpose the two, then two events would simultaneously take place. Circular motion in the yz plane and the yz plane advancing in the x direction because of v cos theta. V cos theta will cause that circle to move in this direction. Yes or no? V sin theta will cause circular motion like this, v sin theta and b. This is the direction of b and this is v sin theta. So then there would be circular trajectory like this, and this circle would advance in this direction because of v cos theta. That is what is going to happen. You know what I'm saying? So circular motion with the circle changing planes at all instants. Plane of the circle constantly changing, but at all times the plane of that circle will be parallel to the yz plane. The b lines would be intercepted by this normally. Yes or no? Now, no matter what, see, Say this is the x direction, huh? Where the B lines are. थोड़ा गंदा हो जाएगा. Huh? See, suppose this was a plane on which I project the motion of the charged particle, charge q mass m on this plane, fixed plane. Say, which means I were to throw light on the charged particle and observe its shadow on this. This plane will not register the actual motion of the particle. What you would see on the plane is that the shadow will execute a circular trajectory. The radius of that circle would be mv perpendicular by qb, would be the radius of that circle. On this plane, if you had to project the motion on this plane, then this plane will not register the actual motion v parallel. It will register only a circular trajectory obtained out of a combination of v perpendicular and b. The radius of that circle would be mv perpendicular by qb. The omega of this motion is good. That means time taken for full 360 degrees rotation on this plane is going to be 2 pi by omega, where omega will still be qb by m. Right? And so on and so forth. Do you all understand this? Now, thank you. What really then transpires is that eventually a non-coplanar motion results, and so on and so forth. See, the particle goes this way, comes back to this point. This is the first point where it crosses the x-axis. Then this would be, say this was O. This will be O1. By the time it goes from O to O1, then on that plane it would have registered 360 degrees rotation. When it goes from O to O1, a point on the axis and back to the axis, right? This is the x-axis. It crosses the x-axis a second time at O1. See, a full circle gets executed. However, the circle would have also advanced. Right? Then it takes up this. It will cross the x-axis again at O2. And between O1 and O2, 360 degrees rotation of the charged particle. That means time taken would be t, capital T, which would be 2 pi by omega between O1 and O2. Between O1 and O2, time taken would be capital T. Right? You know what I'm saying? Because full 360 degrees rotation between O1 and O2 as observed on that projector. Yes or no? So, like I said, omega of this circular aspect of the motion is going to be qb by m. The time period associated with the full 360 degrees rotation, this time you look upon time period as full 360 degrees rotation as observed on that screen, is going to be 2 pi by omega. 2 pi by omega means 2 pi m by qb. Right? And while it goes from O1 to O2, realize that the time elapsed would be this, right? And in that time, it would have undergone an axial advancement. The axial advancement would have been v parallel into t, right? This is the separation between two consecutive points on the x-axis that it crosses, right? Pitch of the helix. This portion is called the helix. This trajectory is called the helix, where it's circular, but the circle keeps advancing. These are various strands of the helix. Helix. The motion is helical in character. The motion is helical in character. H-E-L-I-C-A-L, not H-E-double-L-I-C-A-L. The separation between two consecutive points that it crosses on the x-axis will be the pitch of the helix, right? O1, O2 is the pitch of the helix. And O1, O2 is caused by what? O1, O2 is caused by V parallel, which is V cos theta acting for how many seconds? Capital T seconds, because in this time a full 360 degrees rotation would have taken place and the particle would have come back to this axis of the helix. Yes or no? Got me? Pitch. P and not B. Okay. And this is also separation between consecutive strands of the helix. See, this separation is P, this separation is P, this separation is P, and separation between consecutive strands of the helix, that's also the pitch of the helix, which is the geometry of the helix. Now, again, see, when it goes from O to O1, it takes up this trajectory, this. A full 360 degrees rotation would have taken place on that projector, right? Right? Now if I said, what is the length of this helix from O to O1? So there is a certain trajectory that it has pursued from O to O1? Let's be simple. Good and simple. Has the speed of the particle changed? Has the speed v of the particle changed during the motion? V cos theta and V sin theta. V cos theta has not changed. V sin theta has continuously changed directions. V sin theta has been along the tangent to the circular trajectory at various instants of time. The speed V has not changed. Right? The time taken to go from O to O1 is capital T seconds, with a constant speed V. So the distance covered in that time is going to be V into T, yes or no? So that means the length of this portion for a full 360 degrees rotation is going to be V into T. Yes or no? Constant speed. So the total distance would be speed into time. Right? So that will be the length of this helix from O to O1 or from O1 to O2 and so on and so forth. Right? This S is this from O to O1, the actual distance, the actual length of the helix, right? So this is what transpires. If a particle enters the region of a magnetic field at an angle theta, right? Suppose I have a region in space in which both an electric field and a magnetic field is present. Simultaneous presence of electric magnetic fields in a certain region. Whose was that? Very old fashioned. Change the ringtone and allow it to not spring into action while I am in action. Switched off? Is there any other phone which has the prospect of doing the same? No? If there is, take care of it right now. Otherwise, I will have to take care of you then. My remarks from the first ring to the second ring could only be escalated and stronger and intense. And therefore, the next time the remark will not stay confined to change your ringtone. Right? I will add some frills to it. I will add some flavor to it. Very sweetly, I will communicate very harsh ideas. Okay? So make sure that you don't become the brunt of my attack. Right? So I hope your phones have gone into hibernation for a little while. Shall we proceed? Okay. Now, simultaneous presence of an electric and magnetic field in a region. That is what I'm going to examine. Some common situations. Say, there is a region in space where there is an electric field E, which is E naught j cap, constant electric field E, which is E naught j cap, means in the y direction, and constant magnetic field B, which is also in the y direction, say. B naught J cap. Both in the y direction. All right. Now, say this is the x direction, say this is the z direction, and y, z. So y must be going into the plane of the board. This is the y direction. This would be the y direction in which E naught and B naught are simultaneously present. Right? This is the case we are going to examine. We would release a charge q of mass m. Let's assume q is positive. Mass m starting from rest at the origin of coordinates. All right. We will examine the motion of this particle in this region. Fine. Now, to avoid clutter, can I just remove this and deal with that? Just remove this so that my diagrams are better understood. Let me look at what the magnetic field does. Let me look at what the electric field does. And let me superimpose the effect of both. That would be the blueprint that I am going to embrace. Fine. So let me just look at the impact of B naught. Impact of B naught. And say instead of rest, let me get a little more general. Let me impart it a velocity, say V naught along the x-axis. Say initial velocity is V naught, I cap is the initial velocity. Right? Now, do you realize V naught is like this? B naught is in the y direction which goes into the plane of the board. Yes or no? Now V is perpendicular to B. So V and B will connive to produce a circular trajectory. V and B will connive to produce a circular trajectory. Why? Because V is perpendicular to B. Right? Now, if there is a circular trajectory in the pipeline, then the plane of the circle must be intercepted by the B lines normally. If the B lines are in the y direction, then XZ plane must be the plane of the circular trajectory, yes or no? Right? So this will produce plane of circular motion. Is the XZ plane. Is the XZ plane. Why? Because B lines are in the y direction and the XZ plane is intercepted by the y direction normally, perpendicularly, right? Now, that means the domain of action of the B magnetic field is the XZ plane. It does nothing in the y direction. It does nothing in the y direction. It keeps its action confined to the XZ plane. Whereas the electric field acts only in the y direction. So therefore its action is confined to the y direction alone. Therefore, one thing, they are not interfering with each other. Whatever is happening in the XZ plane by the magnetic field has nothing to do with whatever is happening in the y direction by the electric field. Therefore their impacts, their effects could be superimposed with a great amount of convenience and simplicity. Right? So what I do is, I examine, and the electric field is doing nothing in the XZ direction. Right? So I examine what is happening in the XZ plane independently by the B lines, magnetic field. Right? First thing. And then I would look at how the electric field interferes to produce motion in the y direction. Clear? But first things first. So displacement in the x direction and the z direction are only courtesy magnetic field B. Displacements in the y direction are courtesy electric field. Right? So let me find out the displacements in the x and the z direction courtesy magnetic field, and displacement in the y direction courtesy electric field, and consolidate them together. Is that okay? Now, forget the electric field for a while. Let's look at the effect produced in the xz plane alone. V naught is like this. V naught is like this, and B is going into. There would be a circular motion produced in the xz plane. Now, if V is like this, B is like this, V cross B is upwards. Assuming Q is positive, if V cross B is upwards, that means the direction of the magnetic force is upwards. That means the center of that circle will be somewhere here. Yes or no? So the center of that circle in the xz plane would be, let's say, some C here. Right? Where OC will be the radius of the circle. Yes or no? OC will be the radius R of the circle, which would be mv naught by qb naught. mv by qb? Yes or no? This is the radius R. Now, the magnetic force is always perpendicular to V naught. It will not change the magnitude of V naught, but it will continuously change the direction of. Therefore, its speed in the xz plane will remain V naught. Its speed in the xz plane will remain V naught at all times. So it undertakes a circular trajectory. It goes in time t. Let's say the particle comes here. Its speed remains V naught, tangent to this circle. Tangent to this circle. Yes or no? It describes an angle theta at the center. Describes an angle theta at the center. The angular velocity with which it executes this circle is going to be qb naught by m. That's the angular speed with which it will execute this circular arc in the xz plane. qb naught by m. Right? So in t seconds, the angle described at the center, theta, would be omega t. So this is at an instant of time t. At an instant of time t, the angle described at the center, theta, would be omega t. So theta is known to us, omega is known, omega is qb naught by m, so I know theta. T seconds later, right? Now, this is small r, the radius of the circle. This is also small r, the radius of the circle. Right? Now, do you realize that the x coordinate of the particle t seconds later would be this, which would be r sine theta? That would be the x coordinate, r sine theta, yes or no? This would be the z coordinate of the particle t seconds later, which would be r minus r cos theta. Right? So which means t seconds later, at an instant of time t, the particle p has x and z. The x coordinate would be r sine theta, where theta is omega t, r is mv naught by qb naught, right? And theta is omega t, right? The x component of the velocity, realize that this angle must be theta, right? If the radius makes with the vertical at an angle theta, a perpendicular to the radius will make with the horizontal an angle theta, right? So the x component of the velocity, Vx, would be v cos theta, v naught cos theta. Speed v naught will not change with time. Theta is omega t. Omega is qb naught by m, right? Now, this would be the z coordinate of the particle, which is going to be r minus r cos theta. Yes or no? So the z coordinate of the particle t seconds later is going to be r minus r cos theta. Theta is omega t, r equal to mv naught by qb naught. Z is known. The velocity in the z direction would be this, which would be vz, v naught sine theta. So velocity in the z direction is v naught sine theta. Theta, like I said, is going to be omega t. The magnetic field confines its action to the xz plane. It does not interfere with the y direction, which is the domain of action of the electric field alone. Yes or no? Now, let's then examine what is happening in the y direction. We have examined everything that is happening in the x direction. X coordinate t seconds later, x component of the velocity t seconds later, z coordinate and vz t seconds later. We know everything about this. I want to know the y coordinate of the particle t seconds later. I would want to know the y component of the velocity of the particle t seconds later, right? These are two other things that I want to add to this. So now that's simple, because in the y direction it's only the electric field that is acting. The electric field exerts a force q e naught in the y direction, therefore produces an acceleration q e naught by m in the y direction, right? So in the y direction, the electric force that acts is q e naught divided by m. That's going to give me the acceleration in the y direction, right? So displacement in the y direction, initial velocity in the y direction is 0. So displacement in the y direction t seconds later is going to be half of ay into t squared, constant acceleration in the y direction, right? The velocity in the y direction t seconds later is going to be ay into t. Initial velocity in the y direction is 0, ay is q e naught by m, etc. Yes or no? So I know the y component of the velocity, the y coordinate of the particle, x coordinate, z coordinate, x component of the velocity. So I know what exactly the particle is doing, right? It's not going to be helical, because the velocity in the y direction is not remaining constant. Pitch will go on increasing. It's going to be like a helix with increasing pitch, because increasing velocity, so it will travel greater and greater distance in the y direction in a time capital T, which is 2 pi m by qb, and so on and so forth. So it's going to be a pitch with increasing helix in the y direction, right? So that's the trajectory. Now let me change the situation a little bit. This was E and B both in the y direction. Let me talk of E and B perpendicular to each other, right? Let's examine the case where E and B will be perpendicular to each other. Fine. Say I have B naught like this in the y direction, and I have E naught along the x axis. E and B are perpendicular to each other. Say B is B naught j cap, and E is, say, E naught I cap. This is the y direction. E naught and B naught, this is the y direction, by the way. E naught and B naught are perpendicular to each other. And the particle starts from rest, charge q, mass m. Charge q, mass m. All right. Now, realize that E naught will build velocity in the x direction. Initially, the velocity of the particle is 0, so magnetic force will be 0. Right? So initially there would only be a force in the x direction, which will cause a velocity to be built in the x direction. Velocity in the x direction will get built. Now once you have a non-zero velocity in the x direction, then this velocity will then combine with this b naught to produce, to at least try and impart it a circular motion. That means what this v and b will do is, see, there is this V like this, and there is B going into the plane, right? So V cross B would be in the Z direction. V cross B would be in the Z direction. Just a little time later, when the velocity in the X direction has built, then V is like this, B is like this. So V cross B, the magnetic force would be in the Z direction, and that force will build velocity in the Z direction. So there is built up of velocity in the X direction, there is built up of velocity in the Z direction, there is no velocity in the Y direction ever built up for this situation. Therefore the motion is confined to the XZ plane. It's planar motion. More complicated situation, but simpler motion, right? The motion is confined to the XZ plane, right? So at any instant of time t, the velocity of the particle would be like Vx I cap plus Vz k cap. No velocity built up in the Y direction. See, after a while, when it has a velocity in the X direction, Vx is like this, B is into the plane of the board, right? So velocity V cross B is like this. So magnetic force is in the Z direction, which will cause an acceleration in the Z direction, which would build up a velocity in the Z direction. So there is no built up, all that I was suggesting was that there is no built up of velocity in the Y direction. At any given instant of time, it will have a combination of Vx and Vz only. Sorry? No. The point is, in that direction, if you look at the total work done, that's going to be 0. It will change the direction of motion, isn't it? So of the total V, it will change the direction of motion, so it will build up a velocity in the Z direction, isn't it? Of which, this is anyways accelerating, this is doing work and building up kinetic energy. But this by itself, B by itself, is not changing kinetic energy. It is only taking something out of the original kinetic energy and, building up velocity in the Z direction. It's not going to change the speed anyways, right? So V is Vx I cap plus Vz k cap. That's a velocity profile. I want to find Vx as a function of time. I want to find Vz as a function of time. Vy will always be 0. Y will always be 0. The particle undergoes planar motion in the XZ plane alone, right? So let's understand what kind of a motion it is. Clear? Now, the net force that the particle experiences when it has a velocity v, at an intermediate instant t, it has a velocity v. The net force that the particle experiences then is going to be q into E naught I cap, that's the electric force, right, plus q into v cross b. V is like Vx I cap plus Vz k cap cross b. B is b naught j cap. Yes or no? Simultaneous presence of electric and magnetic fields. This force is referred to as a Lorentz force. It's called a Lorentz force. From this is the physics of the problem. Now the rest is mathematics, right? Ordinary algebra, ordinary calculus. Let's obtain Vx and Vz as functions of time, right? Now, can I remove the clutter from here? E naught j I cap, yeah, I cap only. See, F is like Q into K cross J is minus I, isn't it? K cross J is minus I. So we have like a minus Vz B naught, which I can club with this because it's going to give me an I cap, right? K cross J is minus I, which I club with this. So E naught minus Vz B naught I cap plus I cross J is K. So Vx B naught K. Yes or no? Realize that the force is only in the xz plane. There is no force in the y direction. There would be no built-up of acceleration or velocities in the y direction. Motion would be planar and would be in the xz plane. Right? Can I wipe this off? Okay. Now, there is acceleration in the x direction, ax, which would be force in the x direction, which is q into E naught minus Vz B naught by m. That's acceleration in the x direction, right? Which is rate of change of velocity in the x direction. Acceleration in the x direction is rate of change of velocity in the x direction, dvx dt. This will give me force in the y direction. So force in the y direction is q into Vx into B naught divided by m. That's going to be acceleration in the z direction, which is dvz dt. Yes or no? Which is acceleration in the z direction. How about it? Now, what I do is, this is equation 1, this is equation 2. Right? Two unknowns, Vx and Vz. What I do is, let me differentiate this one more time with respect to time. Equation 1, differentiate this with respect to time. When I differentiate equation 1 with respect to time, then I get d2 Vx dt2, right? Equals minus qb naught by m dvz dt. This is what I get when I differentiate equation 1 with respect to time. d2 Vx dt2, qe naught by m is constant, so minus qb naught by m dvz dt is what I get, right? But dvz dt is qb naught by m into Vx. This dvz dt I can take from equation 2, which is qb naught by m into Vx. So this dvz dt that I have here, I can source from here and write as qb naught by m into Vx. Right? Plug in 2 into 1. So this would give me minus qb naught by m whole squared into Vx. Yes or no? Which then is a familiar equation. See, when I solve this equation in simple harmonic motion, d2x dt2 is minus omega squared x. What was the solution to this equation? X is some a sine omega t plus phi was the solution to this equation. Yes or no? That was the solution to this equation. Right? Now, it's the same equation with omega being qb naught by m. Right? Omega squared, omega being qb naught by m. And instead of x, you have Vx. Yes or no? So, the solution to this equation would be just like the harmonic oscillator, Vx would be some V naught. Instead of a, you have V naught sine omega t plus phi, where omega is qb naught by m in this case. Omega is qb naught by m in this case. Yes or no? Same kind of solution? Are you lost or are you okay? Huh? Now, realize that the particle started from rest. At t equal to 0, Vx was 0. So if you put at t equal to 0, Vx is 0, you'll get phi as 0. Right? Because the particle started from rest. If it had not started from rest, then at t equal to 0, let's say Vx would have been some V1 and you would get some other value of phi. Just to simplify the algebra, I took the particle starting from rest. But if it didn't start from rest, only this phi would have changed. Right? So then, since in this case at time t equal to 0, particle started from rest, phi turns out to be 0. So then this is what the motion is, where V0 is still to be handled. V0 is the amplitude of Vx. V0 is the amplitude of Vx. Now realize that when the particle started, only force that it experienced at time t equal to 0 was QE0. Because it started from rest, there was no magnetic force at the origin, there was only an electric force. Therefore, it had only an acceleration in the x direction, which is QE0 by m. At time t equal to 0, the only acceleration that it had was QE0 by m, because there was no magnetic force, right? So at time t equal to 0, Ax was QE0 by m. At time t equal to 0, Ax was QE0 by m, yes or no? Which means, what is Ax? Ax, as you can see, at any given instant of time would be V0 omega cos omega t at any given instant of time. Right? V0 omega cos omega t. Ax at time t equal to 0 is like V0 omega at time t equal to 0. Yes or no? Which is like QE0 by m, which I showed was QE0 by m at time t equal to 0. And this gives us an opportunity to obtain V0, because omega is QB0 by m. So this gives me omega QB0 by m is QE0 by m, giving me V0 equal to E0 by B0. Yes or no? Sparsh. Did you understand this acceleration? At t equal to 0, what was the acceleration? Put t equal V0 omega, but we already obtained acceleration at time t equal to 0 as QE0 by m. So this must be QE0 by m. Replace this omega by QB0 by m. Omega by QB0 by m. So this gives me V0 equal to E0 by B0. Sounds good? Now I have complete knowledge of my Vx. Vx would be E0 by B0 sine omega t, where omega is QB0 by m, right? Vx then is E0 by B0 sine omega t. Right? But what is Vx? Vx is dx dt. Sine omega t. This is done with the objective of finding x as a function of time. Vx written as dx dt, velocity in the x direction. Right? So this dt you bring in here. Integrate both sides. At time t equal to 0, x was 0, particle started from rest. At time t equal to t, x became x. This will give me x equal to E0 by B0 omega into 1 minus cos omega t. That's the x coordinate of the particle as a function of time. Yes or no? Now, so I know the x component of the velocity at any given instant of time. I know the x coordinate of the particle as a function of time. Now what I do is I come down to this equation to get Vz as a function of time. The velocity in the z direction as a function of time. So then dvz dt, this was dvz dt, sorry, dvz dt. dvz dt is like a qb naught by m into vx, where vx is e naught by b naught sine omega t. Right? So this b naught gets cancelled, and when you integrate, you get vz equal to e naught by q e naught by m, omega will come here, into, at t equal to 0, vz was 0, so it will become 1 minus cos omega t. You can check, because this will give me minus cos omega t by omega, that omega comes here, at t equal to 0, vz was 0, at t equal to t, vz becomes some v. This is what you will get. Right? Where omega you can write as, I hope I don't have to carry out detailed working of this, right? You followed this. Omega I can write as qb naught by m. So essentially m omega naught is qb naught. M omega naught is qb naught. So this m omega naught I write as qb naught. And you expected the amplitude to be dimensionally e naught by b naught. E naught by b naught therefore has dimensions of velocity. Do you realize that? Dimensionally e naught by b naught is meters per second, right? So you did expect this e naught by b naught. If it came there, it should have come. If it came in vx, it should have also come in vz. This or some constant times e naught by b naught, right? So that's vz, and this you can write as dz dt. These are not results to be mugged up. I was just telling you how to deal with a situation of this kind. Don't mug up these results, okay? So dz dt, if you integrate this, again, you know, you will get like a t minus sine omega t by omega. At t equal to 0, z was 0. At t equal to t, z was z, and you can get z as a function of time. The nature of this curve in the xz plane, I'm going to come to this in curve tracing, but too early to, you know, talk about details of this curve. The xz plane, it's a cycloid. The motion is a cycloid. The path traced by a point on the rim of a cycle which rolls without slipping. If a point on the rim of the cycle moves, then the path it traces is actually this path, which is a cycloid. I'm going to come to it when I'm doing curve tracing, but not now, right? It's a cycloidal path. Cycloidal because it represents the path traced by a point on the rim of a cycle which rolls without slipping. That's why it's called a cycloid. Cycloid. X versus z is going to be a cycloid. Z you can find after integrating this, and so on and so forth. Got me? See, obviously you can see that if a charged particle enters the region of a magnetic field, it is likely to get deviated. It's likely to get deviated. So, say if this is a strip in which there is a uniform magnetic field B going into the plane of the board. Right? And there is a charge Q mass M. And say this length is L. This length is L. The strip is of length L. Charge enters this region with a velocity v naught. Say Q is positive. Then very clearly V is like this, B is into the plane of the board, so V cross B would be like this. It will execute a circular path in this region, right? It executes a circular path in this region, which is this. Its speed will not change. Why? Because the kinetic energy will not change, right? The center of the circle will be somewhere here. So the particle P enters here, and this would be the radius of the circle, right? This would be the radius of the circle. V naught and B naught are perpendicular to each other. So the trajectory would be circular, where this plane of the circle would be intercepted by the B lines normally, right? So the radius of the circle would be what? MV naught by QB naught. Say B naught is the magnetic field in this region, uniform magnetic field in this region. Right? And it will have an angular velocity omega, which would be QB naught by M is going to be the angular velocity with which it executes this arc, right? This is the center of the circle, because this is the direction in which it experiences QV cross B. V is like this, B is like this, so V cross B would be towards C, right? It subtends an angle theta at the center, its angular deviation is theta, where theta is given by omega t. In this case, L, which is this, R, which is this, L is smaller than R. L is smaller than R. And then it will exit in this region, and the original direction of V was horizontal. Now V makes an angle theta with the horizontal, isn't it? If the radius makes an angle theta with the vertical, a tangent at that point will make an angle theta with the horizontal, right? So theta is the angular deviation produced. Theta is the angular deviation produced, right? Where how does one obtain theta? Theta is obtained as sine theta equal to L by R, where L would be known, the length of this, the width of the strip is known, R can be computed from these considerations, so the angle of deviation is known, right? And obviously for this to exist, for this to exit in this region, L must be less than R, right? So theta can be computed from these considerations. Once you know theta, then the residence period in this, the residence period in this region is going to be, the residence period is in this region is going to be what? Theta divided by omega. Theta is the total angular deviation. This is the rate at which theta changes. So this is the time it takes. Theta we have computed. Omega we know is QB naught by M. This will give me the residence period in this strip. Clear? Yeah, it will exit into this region and it will then go undeviated with a velocity V naught. Sounds fair? I'll tell you. Yeah, I'm just going to tell you. That's exactly what. Suppose L is equal to the radius R. Then, please notice if L, the width of this strip is equal to the radius R, it enters with a velocity V naught. Hello? Don't get antsy. Then what will happen is it will go this way. Sorry, badly drawn, huh? This is the center C. This L turns out to be the radius R. It will exit like this with a velocity V naught leftwards now, and the deviation produced would be pi. Deviation produced would be pi. This happens not only for L equal to R. If L was greater than R also, the same thing will happen. I hope all of you understand this, right? So if L was greater than R, then the trajectory would be like this. This is the case where L, this strip length L is greater than R, the radius. Strip length L is greater than R. So for L greater than or equal to R, it will execute a semicircle and exit. The deviation would be 180 degrees. Deviation produced is going to be 180 degrees. Theta will be pi by 2. It is pi by 2. But then it's not executing. See, when it comes here, do you realize that theta is 90 degrees? So, yeah, theta is 90 degrees when it comes to this point. isn't it? And it will go this way. Right? Yeah. Because see, hello, you've been sitting, I've been standing, and I've been talking, and I've been focusing, I have been concentrating. Some of you have lost concentration, some of you, most of you, all of you are sitting comfortably, and therefore there is no reason for you to lose out on patience. Okay? Listen to me. Yes, now it is a question. Yes, it will not execute a full circle in this case, because once it exits, it will experience no more. In a region in which, you know, there is a magnetic field to sustain that full trajectory. It may not be infinite, it may be just this region, like this, and it may execute a full circle. Right? See, even if you turn it to be infinite, even if this turns out to be infinite, but if it enters like this, it will not execute a full circle. Isn't it? That's the point. Now, give me 2-3 minutes, I'll let you go. Okay, I'll tell you a case also. It enters at an angle theta, this region, right? Let me tell you that case. Can I wipe this off? One last case, please. Come on. Say, one last bit. Come on. This is the strip. All right. Magnetic field here. L less than R. All right. Say this time it enters this interface this way with the velocity v0 at an angle alpha. Right? B goes into the plane of the board. Say B0. Charge Q positive, mass M. It enters this interface this way now. Okay. Now do you realize that its velocity is like this? V0. V0 is like this. B goes into the plane of the board. B goes into the plane of the board. Right? B goes. So do you realize V cross B would be like this? That means this time this would be the direction of V cross B. If V is like this, B is like this, this would be the direction of V cross B, and therefore this is where the center C of the circle lies. This center C now doesn't lie on this interface. It lies in the region from which the particle enters, right? And therefore it will execute a trajectory like this. Its speed will remain the same because the magnetic field is incapable of changing the speed. Its radius will be R, right? Isn't it? This angle is alpha. From symmetry again, you know, that's ordinary geometry. If this is alpha, this is also alpha. Do you realize what would this angle be? 2 alpha. Yes or no? This will be 2 alpha. Do you all relate to this? Okay. The radius R of the circle, V is still perpendicular to B. V is like this, B is going into the plane. So radius of the circle is going to be mv0 by qb0. The angular velocity is going to be qb0 by m. Alpha is given. Deviation. Now this angle is 2 alpha. So time taken, residence period is going to be, well, the total angle subtended at the center 2 alpha divided by omega. The rate at which alpha is subtended, right? So 2 alpha is the total angle subtended at the center divided by omega. That's going to be the residence period in this. The arc length is going to be r 2 alpha. If this is the arc length s, then this is going to be r into 2 alpha. Alpha, of course, is given to you. R you can compute from these considerations. Right, so that's a brief one on deviation of a charged particle when it enters a strip of uniform magnetic field, right? This much for today. Have fun, but stay out of trouble. We'll see you on Wednesday, okay? Take care, bye-bye.